Yeah, hello. Let's start lecture 7. So today, first we will talk about the sorry application or the method we learned before for double integral. So the application will be focused on the physics. We will talk about the density and the center of mass. Basically, we will not talk about the physical origin of those concepts. We only focus on the computation. And so first, look at the following example. So electric charge is distributed over the triangle region D, triangular region D. So the D is given by the following graph. You have x-axis, y-axis, and the three vertex is as follows: 1, 1, 0, 1, and 1, 0. And so that the charge density at the point xy is sigma xy equals x times y. So the problem is find the total charge of D. Okay, now first let's turn this problem into a calculus problem. So the total charge is given by the integration over the region D of the function sigma xy. Okay, and if you look at the picture, you can view D as type 1 domain or type 2 domain. So I will choose it as type 1. So first, inside you have integration with respect to y. Outside you have integration with respect to x. And to determine the interval, actually you go from outside to inside. For x, you integrate from 0 to 1. And then for y, you see, for fixed x, the y is bounded by two functions. So the top one is y equals 1, and then the lower one is given by, so h2x equals 1, and then h1x for the lower boundary is given by 1 minus x. Therefore, here you have 1 minus x to 1, and inside you have x times y. That's a formula for sigma xy. Okay, now we can integrate it. You have xy squared over 2, and 1 minus x to 1, 0 to 1 dx, and it's 0 to 1 x times 1/2 minus 1 minus x over 2 square dx, and then you have 0 to 1 x over 2 minus x 1 minus x square over 2 dx. We calculate the second item. So here you have 2 x times x squared minus 2x plus 1 dx and equals 0 to 1 x over 2 minus x cubed over 2 plus 2x squared over 2 minus x over 2 dx. So it's 0 to 1. Now you have cancellation. So minus x cubed over 2 and plus x squared dx. And by power rule, it's easy to derive the following formula. 1, 0. Therefore, you have 1/3 minus 1/8, which is 5/24. Okay, you see, although the problem is pretty physical, but all we need to do is evaluate some double integral. Next, so this, so if you change the name, charge, you change it to mass, so you will have total mass, density of the mass, the same thing. And next we discuss another type of problem, find the center. So find the mass and the center of mass of a triangular domain with vertices 0, 0, 1, 0, and 0, 2 if the density function is rho x y equals 1 plus 3x plus y. Okay, let's draw the picture first. X, y, and you have 3 vertices for the triangle. The origin, and then 1, 0, and then 0, 2. Okay, therefore the region is given by this way. Okay, now we can calculate in the same way as above for the total mass. So let's denote the total mass by m. So m can be written down as a double integral as follows. You integrate over d, and then the integrand just the density function. Okay, now your domain is also type 1 domain. You can first integrate y, then integrate x. And then for x, you are integrating from 0 to 1. For y, now you need to figure out the 2 boundaries. So h2x, this is 2 minus 2x. That's the equation for this line. And then h1x, just a 0. Okay, therefore you have 0 to 2 minus 2x. And then inside you have 1 plus 3x plus y. Okay, then we can do integration 1 by 1. So first you have y plus 3x, y plus y squared over 2, and 2 minus 2x 0 dx. And then you evaluate the integrand. You have 2 minus 2x plus 3x, 2 minus 2x plus 2 minus 2x squared over 2. Then we use the distribution law. 2 minus 2x plus 6x minus 6x squared. And plus, here you have 2, 4x squared minus 8x plus 4 dx 0, 1, 2 minus 2x plus 6x minus 6x squared plus 2x squared minus 4x plus 2 dx. Okay, now let's combine the constant term. So here you have 4, and then let's look at the linear order term. So minus 4x. Wait, you have one more. So combine this one. Sorry, you don't have. This is 2. This is squared. Okay, so you don't have linear order. You don't have linear order term. So plus 0 and plus. Now let's look at quadratic term. You have minus 4x squared dx. So you have 4x minus 4x cubed over 3 and evaluated at 1, 0. So you have 4 minus 4 over 3, which is 8 over 3. This is a part 1. The total mass is 8 over 3. Next, we want to calculate the center x bar, y bar of the triangle with respect to the density function rho xy. So just a remark, the center depends on the density function. If you choose different density function, your center will be different. Okay, now let's write down the formula. So here, the center, just a point in the same Euclidean space as the triangle. Since we are in R2, so you should have 2 coordinates for the center. And the x coordinate is given by the following integral. So x times density divided by the total mass, and then do integral. Okay, similarly, y is equal to y times rho xy divided by m dA. Okay, now we use this formula to calculate the center in this problem. This is formula. And so question, leave it to you. Why we have m here. Leave it to you. Formulas. Okay, now in our case, we can figure out the total mass. So inside is integral. So let's look at our domain. So actually, everything is same for computation, for the computation of x bar, except the integrand, you change it to x times rho divided by m. Okay, so we still use the setup here. How to view it as a type 1 domain. So 0, 1 is outside, and inside is 2 minus 2x, and then you have x times 1 plus 3x plus y, dy, and then dx. Of course, the computation a little bit more involved, but should be same, the idea. Okay, so you have inside you have x times y plus 3x squared times y plus x times y squared over 2, 2 minus 2x, and 0 dx. And then you have 1 over m, 0, 1, and x times 2 minus 2x plus 3x squared, 2 minus 2x plus x times 2 minus 2x squared over 2 dx, 1 over m, and inside we use distribution law, 2x minus 2x squared plus 6x squared minus 6x cubed plus x dot 2, 4x squared minus 8x plus 4 dx. And remember, m is 8 over 3, so 1 over m is 3 over 8. And then inside, let's look at there's no constant term, and for the linear term, you have this one, and then this one. So you have 2x plus 2x, so 4x. And then for the quadratic term, this, and then this. So you cancel out. And then for the cubic term, you have this one and this one. So totally you have minus 4x cubed dx, and then you have 3 over 8 x squared to 4x squared over 2 minus x to the 4th over 4, 1, 0, and then 3 over 8 is your answer. Okay, similarly, we can write down the formula for y bar. This is integration over d of the function y rho xy divided by m. And then you figure out m, set up the domain. You have exactly same thing, except you have y instead of x. Okay, then you have 3 over 8 integrate from 0 to 1, and inside you have y squared over 2 plus 3xy squared over 2 plus y cubed over 3, 2 minus 2x, 0, and dx, 3 over 8, and 0, 1, 2 minus 2x squared over 2 plus 3x, 2 minus 2x squared over 2 plus 2 minus 2x cubed over 3 dx. Okay, the following will be some lengthy calculation if you don't like it, you can calculate by yourself or just skip it, but I will carry out all the details in case someone really want to see it. Okay, we use distribution law, and here for this part, you will have 2x squared minus 4x plus 2. And then for this part, you will have 6x cubed minus 12x squared plus 6x. And then for this part, you just have 8 over 3 x cubed minus 3x squared plus 3x minus 1 dx. Okay, then let's combine terms. So first, let's look at a constant term. Here you have 1 negative 8 over 3. So you have 2 negative 8 over 3. Then totally you have negative 2 over 3. And then for linear order terms, minus 4 plus 6 plus 3 times 8 over 3, so plus 8. Okay, 8 plus 6 minus 4, so plus 10. And then for the quadratic terms, 2 negative 12 and negative 3 times 8 over 3, negative 8. So 2 minus 12 minus negative 8, so totally negative 18 x squared. And then for the cubic terms, then you have this 6 plus 8 over 3. So totally you have plus 26 over 3 x cubed dx. So 3 over 8 negative 2 over 3x plus 10x squared over 2 minus 18x cubed over 3 plus 26 over 3 times 1 over 4x to the fourth. Okay, here you don't have this. Instead of this, you have 1, 0. Okay, you plug in 1, negative 2/3 plus 5 minus 18 over 3, which is 6, minus 6, and plus 26 over 12. So we should be 13 over 6. Okay, then you have 3, 8. Finally, you will have so minus 1 minus, here you have minus 5/3, and then equals minus 10/6. So am I right? Let's look at oh, I see. Here some mistake. Here you have actual negative sign. Sorry about that. You have actual negative sign. I will omit the calculation here, leave it to you. In other words, you need to fix all the calculation in the following. Fix it. Okay. Anyhow, after some calculation, you can do that. If you still have trouble with this problem, you can send email to me. We can work together to figure it out. Next, we will continue our main topic, study the triple integrals. And as we did before, we first studied the easiest case. Region B is a box. So in other words, your XYZ, your variable XYZ are bounded by certain numbers independently. Okay, and then the integral we are interested in is integration of some three variable functions over B. And if you want some rigorous definition, you can view it as limit of some Riemann sums, I from 1 to m, j from 1 to n, k from 1 to l, and inside you have ijk x star, y ijk star, z ijk star times dxi dyj times dzk. And you can guess what is the geometrical meaning of this. This just cut your domain into small pieces. And for each small box, for example, if you consider the box here, so you just replace the integral by the product of the value at some point inside the red box and times the volume of the red box, small red box. So there will be the terms here. Okay, of course, you need to take the limit because when you do this approximation, you always have error. But if you cut finer and finer, infinitesimally small, you expect that will be your correct answer. Okay, the definition is good for your understanding of what is triple integral. But for calculation, if you still remember what we did for double integral, we usually just use Fubini's theorem to write the triple integral as iterated integrals. So the Fubini's theorem states the following. If f is continuous, this is just a technical condition. In this class, most of the time, you can assume f is a very good function. You can take as many different derivatives as you want. And okay. So over the region B equals AB times CD times RS. This is just a notation, indicates X is in AB, Y is in CD, Z is in RS. And then the triple integral F over B can be computed as follows. You first take X integration and then integrate Y, then integrate Z. But of course, you can change the order. For example, in this form, we first integrate with respect to X, then with respect to Z, then with respect to Y. And how many different ways we have to calculate, that depends on the order of dx, dy, dz. So you may have dx, dy, dz, dx, dz, dy, dy, dx, dz, dy, dz, dx, dz, dx, dy, dz, dy, dx. If you learn a little bit combinatorics or computer science, you know that's all the possibility of permutation of three objects. Okay, now let's work out some example. So suppose now you have the following integral to evaluate: x, y, z squared dv, and b is given by the following data. X is between 0, 1, y is between negative 1, 2, z is between 0 and 3. Okay, the question is easy. We just write down it as a triple integral. You can take any way you want. So for me, I just follow the order. From 0 to 1 dx, from negative 1 to 2 dy, from 0 to 3 dz, and x, y, z squared. And then you have 0, 1 dx, negative 1, 2 dy, x times y z cubed over 3, 3 to 0. And then if you evaluate before the y integration, you have 9xy. So this will be 0, 1 dx, negative 1, 2 dy. Sorry, you don't have this anymore. You have 9xy squared over 2, evaluate at 2 and negative 1. So finally, you have, when you plug in 2, you have 9x times 4 over 2, and then plug in negative 1, you have 9x over 2. So you have 0 to 1 dx, 27 over 2x. Okay, then you have 27 over 4x squared, 0 to 1. So totally you have 27 over 4. That's a case for a box, but of course we expect the method for more general domain, just like type 1 domain or type 2 domain for double integral. Therefore, we also introduce the following doable case. So suppose you have the following region in 3D, x, y, z. Here is a projection, and then here, let me here is the top, and then here is the bottom, and then the solid is in between them. So how to write down, describe the region, just like what we did for type 1 or type 2. We first set up the formula for the graph. Notice that the blue part, you have two blue parts, each of them is a graph. You can write down u2, z is u2xy, and then for the bottom one, z is u1xy. Okay, of course, then the red one, the solid, is in between u2 and u1. But of course, here you still need to figure out what is the position of xy, and here let's call this region the projection D. So roughly we will see xy then is in D. Okay, so actually that will be our description for type 1 domain. You have xyz coordinates, xy is in some region D. Since it's a 2D stuff, we assume that we already know very clear for all the 2D problem. And then for the actual coordinate z, we assume it's in between u1 and u2. Then you see it's very similar to the case we did before for type 1 domain in 2D. Okay, next, if D can be described in a simple way, like type 1 domain. For example, it's in between AB and X is in between AB and Y is in between G1x and G2x. Then the integral, so we are interested in the integral I over the region, let's call it V, of any function, any reasonable function. Okay, then we can use the forbidden theorem to write down the integral as iterating integral as following. So for x, it's in between AB, and then for y is G1x and G2x. And then for z is u1xy, u2xy, and whatever the integrand is, you have fxyz. This is a general idea. I suggest you to understand the picture instead of remembering the formula, because in reality you will have different description for V, even for D. For example, it might be type 2 domain. D is a type 2 domain. Then you will have y in between some fixed number, and then x is bounded by two functions of y. Then you need to make some modification of this formula. But it's better to have the idea. Okay, now let's work on some example. We are going to evaluate the integral of function z over region E, where E is a solid tetrahedron bounded by the four planes. X is 0, y is 0, z is 0, and x plus y plus z equals 1. Okay, if you draw the picture, you expect the following one. You can compute the x-intercept, y-intercept, z-intercept. Okay, and then to draw the picture, yeah, let's compute x-intercept, y-intercept, z-intercept. So you will have x-intercept is 1, 0, 0, y is 0, 1, 0, z is 0, 0, 1. And then the solid you have is this one. So bounded by the origin and these 3 points. Okay, then to evaluate this, you first project down to xy plane. Then what do you have from the picture, The region is bounded by, is a triangle whose vertices are the origin and 1, 0, 0, 1. And then you have two faces. For the z coordinates, you have two faces. First one is this, so u1 equals 0. And second one is the green part. So let's see. So u2, because the function is, notice that x plus y plus z is 1. Therefore, z is 1 minus x minus y. So that's the equation for the graph for the blue part, for the green part. So u2 xy is given by 1 minus x minus y. And then the blue part, u1 xy is given by 0. Okay, and if you want to know more about domain D, the projection, so let's use this color. This is an easy example we know before, and here we can use G2, G1, and then G1X. We view D as type 1 domain, so G1X is 0, G2X is 1 minus X. Okay, so as a conclusion, the whole solid, let's call it E. E can be described as follows. X is in between 0 and 1. This is from the description of D. And then Y is from 0 to 1 minus X. this is because of this, and then z is in between 0 and 1 minus x minus y. This is because of this. Okay, then your integral I can be calculated as following. Outside you have 0 to 1 dx, and then inside 0, 1 minus x dy, and then 0, 1 minus x minus y dz. And remember your function is z. Okay, now let's calculate. So the calculation will be easy. So z squared over 2, 1 minus x minus y, 0. So 0, so dy. dx 0, 1, 0, 1 minus x dy, 1 minus x minus y square over 2. And now you view x as a constant here. Don't do distribution law, otherwise you are doing some extra work. This is dy, and then you view it as so what do you have? So how to integrate, how to find the antiderivative for this function. So this is y plus a cubed over 3 times 1/2. Okay, so applied here, you have y plus x minus 1 cubed over 6, 1 minus x, 0. And when you plug in 1 minus x, you have 0. And when you plug in 0, you have x minus 1. So minus x minus 1 cubed over 6 dx. You have minus x minus 1 to the 4th over 24, 1 under 0. So totally you have 1 over 24. Okay, so this for type 1. Similarly, you might have type 2 and type 3. But actually in 3D, those notations are quite, how do I say, it's not standard. You may choose the notation by yourself, because you see here for E you can project to x, y. Then for D you can project to x and y. If you want to a rigorous definition, you may have 6 different names or type domains. For example, you had the following one. So as I said before, try to remember the geometry instead of the formula. Okay, so here you project to YZ domain, and X is bounded by 2 graphs. And the type 3, you are projecting to XZ domain. Y is bounded by 2 graphs. Look at the example here. Suppose you have the integral over E of the function x squared plus z squared dv. So where E is the region bounded by the paraboloid y equals x squared plus z squared, and the plane y equals 4. So for this kind of problem, first step is always to draw some picture. You're not required to draw very exact picture, but at least you should understand what is your procedure next. Okay, suppose you have x, y, z, x, y, z, and then record this parabola. The mouse is towards the positive or y direction. Therefore, you may draw it like the following. And then y equals 4, just horizontal plane intersect with this parabola. So I use the yellow color. Okay, then the solid is the region, is the green part. So first step, from your geometric intuition, you should project to the blue plane or the XZ plane, and then you expect the region is the region is region D in XZ plane. XZ. So here is Z, here is X. Okay. I had a hard time to draw the XZ plane. Okay. Suppose we have this one, but actually I think yeah, it's okay. You can draw like this. And then the region D is given by the yellow part. And how to compute the yellow part? We need to solve. So D is given by the intersection is the XZ coordinate of the intersection of blue plane and red paraboloid. Okay, therefore you need to set up this equation, and then you solve it. You will find y is always 4, and then x squared plus z squared is 4. So this will be the constraint. D is bounded here. Oh, sorry, here bounded by this, and then here, let me use this color. The boundary or region D is given by x squared plus z squared equals 4. Okay, then you have several ways to do the following step, but first I would like to introduce a most straightforward way. For D, view it as type 1 domain. Then x is between -2 and 2. This is clear from the picture. and y is bounded by two lines. So u1 g1 is square root 4 minus x squared, and then g2, so this is g2, sorry, g1 is negative 4 minus x squared. Those come from the equation. Okay, so y is between negative 4 square root 4 minus x squared and positive 4 minus x squared. Therefore, your integral can be written down as negative 2 to 2 dx 4 minus x squared, negative 4 minus x squared dz, and x squared plus z squared 4. This is from this part. Yeah, okay, I should say here. So let me use, so u2, so this graph is, so the blue part is given by y equals u2 xz equals 4, and then the red part is y equals u1 xz equals so x squared plus z squared. Okay, then d is given by this, and let's call this as e. So e is given by the following. xy, for xy coordinates, we just copy from d, and then for z coordinates, sorry, here's z. Z, and here's y, x, z. For y coordinate, we derive from this and this. Okay, now we move this up before the evaluation of I, and then we have let's repeat this part. Then we have I equals negative 2 dx negative 4 minus x squared square root 4 minus x squared dz, and x squared plus z squared to 4 dy, and then inside the integrand x squared plus z squared. Okay, at least here we can integrate y. Dz, and then here you have it's a constant, so x squared z squared times y for x squared plus z squared, and therefore you need to evaluate the following integral for square root x squared plus z squared minus x squared plus z squared times square root x squared plus z squared times x squared plus z squared and dz. Then you see we have a little bit trouble here, because first you don't know how to integrate square root of something plus z squared. You do have formula, but it's complicated. And then the other thing is the upper limit and lower limit are square root functions, so it's also complicated. But if you look at the region, we have a little bit involved. But if you look at the region, look at D again, and expect a better method for the next step. So recall, we have some key tools called polar coordinate. And actually it's perfect fit in because your domain now, D, can be described in polar coordinates as following. Because now the equation is x squared plus z squared equal less than or equal to 4. So in other words, what does that mean? If you use x equals rho cosine theta, z equals rho sine theta, then you expect here the equation is given by rho squared less than or equal to 4 or rho less than 2. So the domain can be described by the following. Rho is between 0 and 2, theta is between 0 and 2 pi. Here it's a little bit sloppy, but I'm sure you understand it. We talked about last time, I think. And then for I, we already reduced it to this step. Then we can use polar coordinates. So the domain now is given by 0 to 2, 0 to 2 pi d theta, and 0 to 2 d rho. And don't forget you have actual rho here. And then the integrand is this function. You need to substitute in, you have 4 rho minus rho times rho squared. That's all you have. And now we can simplify it. Inside 4 rho squared minus rho to the 4th d rho, and then you have 0 to pi d theta, and 4 rho cube over 3 minus rho fifth over 5 to 0, and then you have 2 pi times 4 times 2 cube over 3 minus 2 fifths over 5. So it's 2 pi and times 32 times 2 over 15. So 128 pi over 15. Okay, then you see in this type of problem, after we use the deduction from 3D to 2D by viewing it as type 1 domain, there's another trick is polar coordinate for the 2D domain. And this is quite large classes of solid. There are large classes of solid. We can use this method. So this is called triple integrals in cylindrical coordinates. So the stereotype domain for this is given by a cylinder. Okay, then for each coordinate, for example here, each point you can describe by three numbers. First is z coordinate, and then for xy coordinate, you describe by polar coordinates rho and theta. Okay, in other words, in rectangular coordinate, suppose you have x, y, z, then we use the following substitution to describe it. Sorry, here rho. It's not a big issue to write rho or r, and we can solve it, get a inverse transformation. Don't try to remember the formula, you just remember it's combination of projection and polar coordinate. So for this part, you have polar coordinate, and then for this part, it just projection. Stay the same. Okay, now let's look at one problem. So suppose you have, before that, let's do the transformation law for the integral in cylindrical coordinate. Suppose now your region is bounded by the following data. So x, y, z, and so x, y is in D, u1 x, y less than z or less than u2 x, y. And then the D has a better representation by polar coordinates, usually like the following. How to do transformation? So remember, this is the case for the last problem. Just this problem. Just this one. We did the exact same thing here, but now we want to do some systematic study. Okay, then the integral of f over e is given, can be evaluated by the double integral over d, and then inside you have integral with respect to z from u1 xy to u2 xy. And then let's do polar coordinates for d. Then you have alpha, beta, this is for the angle, and h1 to h2, this is for the radius, and then inside you have the function for the height z. Of course, you need to do substitution. F r cosine theta r sine theta z. And here usually if you are familiar with this, then you can write what I did here, and then you have r dz. But if you are not so familiar, I suggest you to use the following formula. They're same, but the key point is don't forget the actual factor r here. This is very important. So in case you you have problem in remember this, then I suggest you to write in this way, z, and then r d theta dz. Combine them as a whole thing. So this is the formula for cylindrical coordinates, and then everything is same except you have some extra factor here. So extra factor is r, and actually later on when we do Jacobi transformation, we will show that not only for cylindrical polar coordinates, for any transformation, in general, you expect an extra factor, and actually you can compute that. We will do that later. So for the purpose of this lecture, we will just use this formula. Now let's look at some example. So first, look at the following one. A solid E lies within the cylinder. X squared plus y squared equals 1 below the plane. Z equals 4, and above the paraboloid, z equals 1 minus x squared minus y squared, and then the density at any point is its distance from the axis of the cylinder. Find the total mass of E. Okay, as usual, we first draw the picture. So first you have a cylinder. You have cylinder given by this, and then you have a plane. I will draw plane later. So first, then you have a paraboloid. And then you have plane. So the plane is z equals 0. Okay, then the region bounded by them is a yellow one, in between these three parts. And actually here you have some coincidence. That is the intersection of blue part and the red part. So let's compute first. I will show you. So you have x squared plus y squared equals 1, and then z equals 1 minus x squared minus y squared. Then you have z should be 0, x squared plus y squared equals 1. And then what does that mean? That means the intersection of blue and red lies, this computation lies in green plane. Yeah, so this is just a coincidence that simplify our calculation. Otherwise, you have some extra boundaries, but you can still do that in this way. Okay, now let's project down to D. Project down to XY plane. Then you expect, let's draw this as color. Everything should be inside this color part, and then the color part, the formula is given by this one. So D, D is given by x squared plus y squared less than or equal to 1, defined by. And then what is the region? Then you see now you have two boundaries for the solid if you view it as type 1 domain. So the lower boundary is the green part, and therefore u1 xy z equals u1 xy, which is 0. And the up part is, from the picture, is the blue part, it's the blue one. So z is u2 xy is given by 1 minus x squared minus y squared. Okay, then the integral can be written down as integration over d, and inside you have z integration. And recall what is the density function. So let's first write down density function here. And then what is density function? Because this is distance for the axis of the region of the cylinder x. So I don't have actual color. Okay. So the distance equals square root x squared plus y squared. Okay, so here for you have square root x squared plus y squared dz. And then in the following, you will see you have symmetry between x and y. That means if you change x to y and y to x, the integral is the same. Then the domain also is symmetric. You can rotate it, so you use polar coordinates. And then before that, we need to figure out the description of D in polar coordinates, because D is given by x squared plus y squared less than or equal to 1. Then if in polar coordinates you have this one. Okay, now use the formula here. You have the integration is from 0 to 2 pi d theta, and from 0 to 1 d rho, but then you have extra rho, and then inside 1 minus x squared, you should do u substitute 1 minus u rho squared 4. Inside you have rho dz. And then what do you have? You first do z integral. You have z evaluate 4, 1 minus rho square, and then 0 to 2 pi d theta, 0 to 1 d rho square, and 4 minus 1 minus rho square. Here 0 to 2 pi d theta, 0 to 1, 4. So here actually you have rho square plus 3. So outside you will have times rho square, you have 3 rho square plus rho to the 4th d rho, and then 0 to 2 pi d theta. Rho cube, 3 rho cube over 3 plus rho to 5th over 5, 1, 0, and then you have 1 plus 1/5 times 2 pi, so 12 pi over 5. Right. Okay, next let's see one more example. So suppose you have I is given by this formula. It's already iterated integral, then how to evaluate it? So first, we do see symmetry and we expect polar coordinates, but then we need to first figure out the domain D. So recall the D. What is D? So because x is between -2 and 2, y is in between negative square root 4 minus x squared and square root 4 minus x squared, then you have D is actually a disk with radius 2. Okay, then D is given by rho theta. Rho is between 0 and 2, theta is between 0 and 2 pi. Therefore, the integral is 0 to 2 pi d theta, 0 to 2 rho d rho, and then here this is rho, so you have rho and 2, and then you have this is rho square, so rho square dz. Okay, then you have 0 to 2 pi d theta, and rho square, sorry, here you can leave it later. First integrate z cube over 3, 2 to rho, and 0 to 2 pi d theta, 0 to 2 d rho, sorry, here you have mistake, and too fast, rho square z, so rho cube 2 minus rho. This is 0 to 2 pi d theta, to 2 rho to the 4th over 4 minus rho to 5th over 5 to 0. And then you have 2 pi times 32 over 8 minus 32 over 32 over 4, 32 over 5. Okay, and this is 8. So totally you have 2 pi times 8 over 5, 16 pi over 5. Okay, this is for today. Yeah, we will stop here.